Alright guys, let's get started. So for those of you that are new to the class that have added since last week, be sure to grab a syllabus. It's going to come around with the roll. And on the syllabus, remember you can find my email address if you have any questions at all or any feedback at all. We would really appreciate that. This week's speaker is a professor here at the University of Utah in our department with emphasis on nanoscale imaging. Is that right? And
Yep.
today we're going to hear a little bit about that research. He is also the, just told me, the design coordinator?
The chair of the design committee.
Yeah, that's right. The chair of the design committee for the New Crocker Science Center, as well as the interim director of the Center for Science and Math Education. It's my pleasure to introduce today Professor Gerton.
Thanks, Sean. It's a little early for that, don't you think? This could really suck. So, great. I haven't come to speak in the seminar for at least a year, or maybe 2 years, so I'm glad to be here. So, as Sean said, I'm a professor in the physics department. My lab is, and my office now are actually not in this building. They're over in INSEC. So if anything that I say today interests you, if you want to chat more about it, if you're interested in doing a research experience perhaps, or just spending some time in the lab learning from what you learned today, I'm happy to talk to you about that. Just contact me. Sean will have my contact information. It's on the physics department website. You can get it in lots of different places. And I'm happy to chat with you. I really am a firm believer in undergraduate research. And so I've had undergraduates in my lab since I arrived here. I'm in my 11th year at the university. And so anybody who's interested in research, I want to help you find a position either in my lab or somebody else's lab. I think that one of the things that the University of Utah has to offer, you all chose this place for probably a variety of different reasons. But one of the smart things about your choice is that the University of Utah has much more robust research infrastructure and activities than any other university in the state of Utah, and many other universities around the world. So we have world-class research here in sort of all the departments, particularly science and engineering. And this is something which you should try to take advantage of as an undergraduate, because that's one of the things that sets the U apart from other institutions, particularly in Utah. So I encourage you all to do that. So again, if you hear anything that's interesting to you from myself or any other person that talks to you during this semester or last semester, really be aggressive at trying to get into a lab, even if it's just to kind of try to get an idea of whether you want to do research, whether you're interested in science as a career. Degree in physics can lead in lots of different careers, as you know, and you've probably been told already. But in case you want to actually go do science, right? Getting some research experience before you go on to graduate school, for example, is pretty important. So happy to talk to you about that stuff too. As Sean said, I'll talk to you about science today, but I'm also the chairperson of a committee, which is, if you all know, how many of you all grew up in Salt Lake area, Utah? How many of you actually went to the Museum of Natural History when it was here on campus just across the President's Circle here? So that old building, which is before it was the Museum of Natural History, which is now up near in Research Park near Redwood Gardens, it was the first co-ed, that is male and female, library on campus, built in the 30s. So before that, I guess there were men and women were not allowed to go to the library together. It's hard to imagine, but that I guess was the case. And so that was the first co-ed library built on campus. And it's a historic building. It's right on President's Circle. And it's being renovated, or at least the plans are to have it renovated to support some, I think, more interactive sort of teaching methodologies, sort of more modern teaching methodologies that have been researched over a number of years at various places, including to some degree at the University of Utah, for teaching science and math courses. And so there'll be teaching labs in there, there'll be classrooms in there, but none of the classrooms will look like this. All the classrooms will at least be able to, you'll be able to work in groups, you'll be able to push the chairs around and the tables around to work together. I'm chairing the committee that's designing that renovation. And so I'm thinking a lot about those kinds of things too. So if you want to talk to me about learning spaces and education, science education, or give me feedback about your time here at the university so far, I'd love to hear that as well. And finally, as Sean mentioned, I'm now the director of the Center for Science and Math Education, and we're involved in a number of initiatives to push science and math education at the University of Utah, but also in the community. So I'm involved in a lot of stuff. I'd be happy to talk to you about any of that stuff. How many of you are actually first years? That is, this is basically what we used to call freshman year. Okay, raise your hand. Okay. How many of you are sophomores? Second years. Okay, so it looks like between most of you are freshmen or sophomores. Are you all physics majors? Everybody here's a physics major? Okay. And how many of you are in the pre-professional track? So maybe with an intention to go on to graduate school in physics or related discipline. How many of you are in the pre-med track? Okay, and how many are you in applied? Okay, so not, okay. So it's not quite a third, but there's representatives from everything. How many of you are double majoring? Okay, in what?
No.
English, philosophy.
Cool. Philosophy. Cool. We can be quantum mechanics philosopher, I think. That's great. So I think, you know, physics is an interesting discipline. It's an interesting major. It's not like an engineering major where you're going to be trained to do very specific things, you know, a reasonably narrow range of things, but do them very well and have a lot of expertise in a particular thing. It's more about gaining wide problem-solving expertise that you can apply to lots of different kinds of problems. And then if you sat down with a textbook or on the web, you can learn how to, you know, a physicist should be able to figure out how to build a bridge, even though they wouldn't be able to do that as fast or as well, I mean, as fast as a civil engineer would. They should be able to figure that out because we learn how to solve problems in a general way. Okay, so I'm going to try not to do like just a full-on PowerPoint, you know, hit it hard, go through lots of slides. I want this to sort of be interactive. So all of my research lab in general is involved with imaging. So how do we look at things? And I should put look in quotations because there's, when I say that, I don't necessarily mean look with your eyes. There's lots of ways to sort of look at things. But really to how to image things with really high spatial resolution, that is be able to look at really, really small structures, nanometer scale structures. And what I hope to do today is to give you a little bit of a feel why this is challenging. You know, first maybe why it's interesting, like why you would want to do this, why it's challenging, and some potential solutions or some potential ways that you can actually overcome some, well, used to be thought to be fundamental physical limitations on how the smallest objects that you can observe or image, and how we're sort of getting around that now with new techniques and new ways of thinking of things. So I'm hoping that you all will have a bit of an appreciation of how that all sort of fits together. And there's a number of different ways that you can actually image things at a really small scale, and we'll just talk about a few of them. So, you know, the title of my talk, right, is mostly about a particular way of doing this, which we'll get to, which is using lightning rods, so basically using sharp sticks. Okay, so, you know, if I took the little ball off the end of here, something which is sharp in some way of measuring sharpness, and how you can use sharp sticks to actually control light and to image things that are smaller than you would be able to if you didn't use that stick. And hopefully that will become more obvious as you move along. So, you know, this is all the thrust for making more and more precise, higher resolution imaging technologies. It's all about, right, what we're calling now nanoscience or nanotechnology. And this is a relatively modern field, you know, kind of in a self-contained way. But I mean, people have been talking about this for a long time. Richard Feynman, how many people have heard of Richard Feynman? Okay, so famous physicist, Nobel Prize winner, involved in the science, the team that basically created the first atomic bomb. He's also one of the physicists, or maybe the most important person who sort of figured out why the shuttle disaster that happened in the 80s, where basically the shuttle took off and blew up, the space shuttle, why that happened, how that happened, what led to that disaster. So very prominent guy, very interesting guy. And he gave a talk to the American Physical Society back in 1959, the American Physical Society, we call it APS. This is basically the Society of Professional Physics Geeks, right? So this is like, if you're going to go on to be, you can actually join as a student and it costs almost nothing. It might actually cost nothing. And it's an organization that lobbies Congress on behalf of scientists and physicists in particular, and partners with other science organizations to sort of promote science activity and funding. And so he was giving a talk, and really he was really kind of birthed the kind of modern way of thinking about nanotechnology. He started wondering, people at the time were thinking more about big things, like what's the structure of the universe, like what's out there. And he was really thinking more about the other side of the scale, like what's really small things, and how if you could get access to manipulating and imaging things at really small scales, that would be really powerful. You could actually create all kinds of technologies, and you could learn a lot about how things like biological systems work. So for those of you who are in the pre-med track, or who might be interested in going to med school or something like that, he was really talking about a dialogue sort of between biologists and physicists. At the time, physics was the hot science that was kind of held way up here and was making the fastest progress, making the most contribution to scientific knowledge. People might argue these days that biology is in that role, in the sense that because of technology that was largely enabled by physics, the pace of research and of new knowledge in biology is incredibly rapid at the moment. But anyway, they were he was sort of having this hypothetical dialogue between a physicist and a biologist saying, hey, if you want me to learn how a biological system works, you need to make me a better microscope, essentially. You need to be able to help me look at things at a smaller scale. And nowadays, right, we have lots of different kinds of microscopes that can look at things. And what are the kinds of things which you might look at? Well, I could put a million things up here. I think some interesting things that pop up are viruses. This is a particularly simple virus, which just looks like a stick. But I mean, what is a virus? On the inside, it's got DNA. It's got a genome. It's got proteins that kind of package that genome. And you can see the scale bar here. So this black line here is 300 nanometers, a third of a micrometer. Right? A nanometer is a billionth of a meter. A micrometer is a millionth of a meter. This is 300 millionths of a meter. That's a small thing. And yet you can see structures which are even much smaller than that. Chromosomal DNA. So DNA, under certain conditions, doesn't look like the double helix which we normally think about. That double helix is wrapped around other things. We call this sort of the beads on a string. So the DNA is the sort of thread which connects these things. And these little beads are actually protein complexes which the DNA winds itself around like a spool. And there's a lot of research going on, like, why? What's the purpose of that? And that's typically how, when DNA is actually in your body, in your cells, it's sort of packaged in a very compact way, and it's wrapped around these things. And understanding why that is and how that works, and how, nevertheless, DNA can be replicated so that cells can divide and things, is a very interesting problem, and it's largely pursued by physicists, biophysicists. Bacteria. So, these are bacteria that are swimming around. There's lots of different kinds of bacteria. Here's a E. coli classic kind of bacteria that's been studied a lot. And you look at this and you're like, what is that? So here's sort of the body, and you can see again, this is a micrometer, millionth of a meter. And then you see these filaments coming off, and then they kind of entangle. Well, this thing swims, okay? And when it swims, how does it swim? It doesn't just float around passively. It actually propels itself. The way it propels itself is that these little filaments, since they're helical, if they turn, it's like a corkscrew. It's like a propeller on a boat or on a submarine. That's why they call the propellers on submarines screws. Okay, and so and each individual filament has an actual motor that makes something going around, that makes these things rotate, where it attaches to the body of the cell. And if it turns one way, if they all turn in one way, then these things kind of get together like a big propeller. If they turn in the other way, then these things kind of splay out and basically stop the bacteria, and it changes direction kind of in a random way. So there's like all kinds of amazingly interesting questions about how that system works. And again, largely pursued by biophysicists. And if you look very closely at where this filament attaches to the wall, you see this mechanism. So now we're going from a micrometer to 30 nanometers, and you can see how intricate the structure is. And you can't understand how this works without understanding what it looks like. You can't understand how the system works without being able to see what the components actually look like and how they fit together. Okay, that's sort of the point of this slide. And it's real motor. It's amazing, right? The thing spins. Okay, it's a rotary motor, and there are all kinds of motors. If you've heard from Michael Verschinnen, has Michael Verschinnen come to give a talk yet this year? Michael Verschinnen's a professor in the physics department. He studies motors. He studies motors which walk, largely motors which walk, not that spin, but principle's the same. You can also make things, of course. These days we have technology that allow you to make really small structures. You know, this isn't as small as the bacterium, and it's not as small, but it's still pretty small. It's a little nano guitar. So Harold Craig, this is years old now. This is probably 10, 15 years old now. Makes a little guitar, and these strings are actually made out of silicon. So they're the same material that we are in our iPhones and our computers that make up the electronics, right? And all the technology which goes into carving up silicon wafers, chunks of silicon, into all the little electronic chips and transistors and resistors and all that stuff, that's the same technology that can be used to make these structures. And this thing actually plays. And you know how they play it is they take a laser beam, which is focused much more tightly in this spot, basically focused to the same size as these strings. And if they focus it on one string, the heat that's imparted to the string by the laser, the string heats up, and so it just starts to vibrate, and then they can move the laser beam and they can play. Now you can't hear it, because you can imagine those strings are vibrating incredibly fast because they're so small and thin, right? You know guitar strings, right? The fat string plays lower frequency, lower tone than the smaller strings. So these are really super small strings, and so they, you can't hear them, but you can use a computer obviously to measure that vibration and essentially divide the frequency by some amount so that you can hear it, and you can actually play songs. They did this cool thing years ago, got a lot of press. This is something which we'll be talking a little bit more about today. This is an atomic force microscope probe, which is basically a kind of a long, sort of flexible stick with a sharp point. So this is sort of a very crude version of that. We have some long thing which can maybe bend or vibrate up and down, and then some point at the end or some little object at the end, which is kind of a probe. And we'll talk more about how that's used. You can combine these kinds of ideas of fabricating or synthesizing things, so human-made things, and natural things like DNA. So here's a schematic. This is not a picture. This is just a cartoon, but you can kind of see that this is DNA. And if you look closely, there's a single. So DNA comes in two strands, right? Hopefully this is in people's brains, even if they're not biologists. Two strands that are linked together by these bonds, and if you look very closely, one of the strands, this gray strand, there's a single gray strand that basically progresses throughout this entire structure. And then there are a bunch of smaller, and they've colored them different colors, smaller pieces that make up the complementary, that are complementary to different regions on that. So these different colors basically they call staples. And so they take this single strand of DNA that's the gray, and they know the sequence. They know the sequences of A, C, T, and G, and then they basically design these little short staple pieces. And if you look at, for example, this staple piece, this purple one, right? It's complementary to this region, which is on this part, and this region, which is on this other part. And in between, the gray strand has basically protruded. So basically, it's folded to the DNA in a particular way. So if they know the strand, if they know the sequence of the gray strand, they can actually design a bunch of staple pieces, smaller pieces, mix it all up in a pot. They don't have to place these. They just mix it all together, and by the magic of DNA base pairing, basically this kind of complementary thing will happen, and it can fold DNA into lots of different shapes. So here's where they've taken this is this idea. They've basically figured out from a particular single strand which staple pieces to make to fold the DNA into this shape. You might say, well, why the hell would you want to do that? I mean, why make a nano happy face? And look at the scale bar here, 100 nanometers. So this thing is 100 nanometers in diameter, 100 billionths of a meter happy face. that was made, and there you can see there are probably billions of these. You basically just you put a bunch of DNA in a pot, a bunch of the gray stuff and a bunch of all the stable things. You heat it up, things naturally, spontaneously form these bonds, and then you cool it back down, and you have happy faces. And this is sort of a flat disk with, obviously some places missing to make it look like a happy face. So the point is, there's a lot. We're learning how to exert lots of control. We're learning how to, do really interesting things. Maybe happy face isn't interesting, but of course it was nice to get on the cover of a journal. But I think what you could imagine doing is using this idea to organize other things and to put them in very specific places. And that's kind of what's going on these days with this DNA origami. So the point is here that, I'm showing you, this is actual data. This is an actual image. This is an actual image. This is an actual image. What kind of images are they? Haven't told you. And also, if you look at this length scales here, we're talking about pretty small distances. Just for reference, by the way, the width of this sort of stick, this cantilever, is about the same as the width of a human hair. So you can imagine the sharp point here is amazingly sharp. Okay, I don't want to talk about that. Okay, so how do we see these things? Well, you all know kind of in general probably about optical microscopy. You've probably used a microscope, or at least seen one used before. Kind of might look like this if you walk into a biology or chemistry lab or some physics labs. And you can use these microscopes to do all kinds of cool stuff. But the limit, to how small the thing that you can look at is about 300 nanometers with such a microscope. So if we go back, this is obviously not an optical microscope image, because the whole thing is 100 nanometers, and these little features are much smaller than that. And I just told and an optical microscope can only see things that have features about 300 nanometers in size, and we'll get to why that's the case. Okay, but there's other really important features of optical microscopy which make it very, desirable to use, particularly in biology. Okay, you can use electron microscopy. So electron microscopy is where, instead of using light or photons to do your imaging, you basically beam electrons, which are little small particles. We all know what electrons are. But instead of these electrons being in atoms, where they're normally attached to the nucleus, orbiting the nucleus, you can actually have free electrons that you accelerate with electric fields and magnetic fields, and basically form them into a narrow beam, and basically put that, what we call raster, or scan that beam over a surface, and by what comes back out, those electrons being reflected, or what gets transmitted, or lots of other different ways that you can measure. You can actually measure structures, but electrons are really, really small, okay, especially compared to the size of a photon, okay, which we'll get to. And so you can use electrons to look at much smaller stuff. So here's something which was made by electrons, but also imaged by electrons. And if we go back to this, these images here are electron microscopy images. So this guitar the computer has been used to take the electron microscope data and convert it into something which looks like an optical image. But the data, how you actually acquire the information which leads to this rendering of this guitar was using electrons. And the same thing here. So the electron microscope by now, and the first slide I showed you with the famous physicists, talked about the electron microscope. So the electron microscopes have been around for a long time. And now we also have atomic force microscopy, which has been around for the last 20, 30 years, I suppose. It was invented, I guess, in the mid-'80s or something like that. And here we're talking about imaging by field, right? We're not actually using particles of light, photons, or electrons to create an image. We're actually sort of poking around, and I'll get back to this. And this is so this basically this kind of technology allows you to image the structure of surfaces, and that's kind of what it does. You can manipulate things a little bit too. And this image here of the happy face was taken with an atomic force microscope, or AFM. Okay. Any questions so far? No? People aren't asleep yet. That's good. It's mostly nuclear waves. Okay, I don't want to go to the atomic force microscope yet, but I'll keep that up there just so. So I want to know, I mentioned that for an optical microscope, the resolution limit is something like 300 nanometers. Okay? So how many people have taken physics 2220 or 3220? How many people are in it right now? Okay. So have you gotten to the point of talking about like capacitors, electric fields and stuff, capacitors, static electric fields? Yes? Okay. How about waves? Have we talked about waves yet? A little bit? Okay, so, you know, why is it that an optical microscope can't look at things smaller than a few hundred nanometers? That's the fundamental question. Because if it could, then why invent? Why have an electron microscope? Why have all these other technologies? So I want we're physicists, so we always have to ask that question. We keep developing technology, no matter how hard we try. The optical microscope can't see any smaller than 300 nanometers, and I should say that over the several centuries, many decades of optical microscopy, lens-based microscopy, right, using lenses to image things with light, right, up until about 20 years ago, 30 years ago, all the improvements, all those decades of work and investment of research and time and effort and money, basically all they did was push us closer and closer to this roughly 300 nanometer limit. Okay, and then it basically stops. So the microscope that you buy now is essentially the same as the microscope that it was invented, several hundred years ago, in the working principle and in its capabilities. Okay, and so all the investment and the reason why they're expensive is because there's all kinds of other things that go along with it. But so why is this? What is the fundamental issue here? Does anybody know? Have an idea? Yeah. Okay.
Wavelength of visible light.
Wavelength of visible light. Okay, that's definitely the right way, and the size of a photon. Those two things basically mean the same thing. But what is it about the wavelength of light that basically makes that a limit? Okay, so let's go through this a little bit. Find the right place. Okay, so here's a simple microscope, a simple lens, or a diagram of a simple microscope system or lens system. Right, you have some object, and you have a lens, and that lens somehow creates an image on the other side of the object. Right, so if you think about it carefully, what you'll conclude is that every point on the duck, on the object, so imagine first of all, this is not a glowing duck, it's not like a luminescent duck. You have to shine light on the duck, right? I mean, otherwise it's not itself emitting any light. It's basically just scattering light. So I'm not showing that part. So basically you can imagine that the duck has light bathing it, from all angles so that it's being illuminated. And what we're seeing is the light which is essentially being scattered or reflected off the duck. And every point on the duck kind of scatters light in some sense in every direction. Okay? But of course, only some of the light coming from, let's say, the duck's head gets captured by the lens. That is, if you think of light as rays, and you think of the rays emitting from each point on the duck, and I've drawn 3 specific points here, on the head, in the middle, and at the bottom. If we think about the red rays, right, the light that's, a ray is meant to represent the direction of a photon. It's meant to represent the direction of the wave, of the light wave. And if light's going off in all different directions, only rays which are sort of between this, within this cone that's defined by these 2 exterior light rays actually hit the lens. All the other ones just miss the lens, and so we don't even think about those. And then what the lens does, right, is fundamentally is that it bends those rays in such a way that they come back to another point over here. And so there's a one-to-one correspondence between the point on the duck's head on the object and the point on the duck's head on the image. And as I've shown this, right, it's an inverted image. Same thing for the middle of the duck, same thing for the bottom of the duck. And these different colors aren't meant to represent actual colors. They're just meant so that we can keep track of the rays. Right, so light from every point on the lens maps to every point on the image. Okay? And if light were, and we know, right? How many of you all have the thin lens equation? Who knows the thin lens equation? I'll get 1 over I plus, no, 1 over O is equal to 1 over F. So this is the distance from the lens to the image. This is the distance from the lens to the object. This is the focal length of the lens. It's a characteristic of the lens, and you can make lenses with different focal lengths. So this is what tells you like how far away an image is going to be if you know how far away the lens is from the object. Okay, this is, if you haven't learned this, you'll do it later in 3210 or 2210. Okay, and this is a very useful formula. And the other thing to keep in mind is that the magnification is equal to the image divided by the object distance. Okay, under most circumstances. So if we want to magnify something more, right, we just have to change these distances, and that'll give us a bigger magnification if we do this right. Okay, so you might say, well, damn, I mean, why don't I just make this bigger and bigger and bigger, and then I can see smaller and smaller things, right? That makes sense, right? So why does that break down? I mean, it's for real. You have to trust me at this point, but it's for real that microscopes actually can't resolve structures. Traditional conventional optical microscopes can't resolve structures smaller than about 300 nanometers. But there's no limit to the magnification that you can achieve, even with a single lens. You just have to change the distance between the object and the lens, and you'll get a corresponding change in the image distance. And if you do it right, you can get a magnification which is approaching infinity. So a really super small point should map to a much bigger point in the image. So why is that not sufficient?
The light itself can't display all the image. It kind of goes past it. Wavelength is too wide.
Wavelength is too wide. Okay, that's kind of qualitative, yeah. That's basically right, yeah.
Yeah, it's not the problem with the microscope. It's that you need to have a large enough object in order to interact with that size of light. So if you're using light that's around this 300 nanometer, then it's not going to interact with things.
Okay, so what happens if I replace my duck with just 2 points? And each of those points were molecules. And those molecules, which we'll approximate as infinitely small points. Okay? And each of those molecules is actually emitting light in all directions. Okay? That actually happens, and we do that kind of stuff in my lab. You can image single molecules. So that's kind of getting to the right place, but that's not quite the right answer. Okay, so, people are kind of understanding that it has something to do with the wave nature of light. Okay? So light is a wave, not a ray. So what does that mean? It means that when it travels, it might travel in a particular direction, and we can define that direction by a ray, basically a vector which is pointing in a particular direction. And but actually, what's physically happening, right, is that there's a disturbance, a wave. Okay, there's an electromagnetic field which, in time and in space, is oscillating. Okay, in a sinusoidal wave. Okay, and you can't really define the size of light, but you can define the wavelength, because if I was able to take this laser beam and take a high-speed camera, higher speed camera than exists, and take a picture of the light wave, the laser beam, like let's say I have some dust in here, so you can actually see the laser beam going all the way from here to there. You took a picture of that at a particular point in time, right? If you're able to capture it quick enough, what you would see is there would be a place where the wave was 0, a place where the wave was maximum, the minimum, the maximum, minimum, just like I've drawn here. And the distance between two successive maxima or minima is the wavelength, and we call that lambda. So that's what the wavelength is. Okay, now what does that mean? Well, when we're talking about imaging, we have to think about how. So if light's not just rays, but it's waves, we have to think about how those waves come back together at the image point. So we have, for example, let's back up real quick. Let's imagine that we're thinking about these two rays, this one and this one, coming back to form the image of the duck's head. Okay, but they're not rays; they're waves, and so we have to draw them that way. So we have this one coming from this direction, this one coming from a slightly different direction, and then again, red and green don't mean different colors here. We're just keeping track. And if you see here, if this is a particular point in space, this if these two things are arriving right here, what you notice is that both of these waves are in phase in the sense that, when this one is maximum, so is this one. When this one's minimum, so is this one. And so essentially we know what that means. That's superposition, and it's called, constructive superposition or constructive interference. And basically what will result is that you'll get a wave which has, the sum of these two amplitudes. So you get something that's even stronger, even brighter. Okay? If you have a situation where the two waves that come together, what did I just do? Wow, this is dying. Two waves that come together are not in phase. So where this one's a maximum, this one's a minimum. Where you add those two together, you add positive x, positive whatever, and negative whatever, you get 0. And so what you'll get is a wave which has a much smaller amplitude, or maybe even 0 amplitude. And this is destructive superposition or destructive interference. And so when you have two waves coming together to the same point, depending on their relative phase, they'll either create something which is a bigger wave, that is a wave with larger amplitude, that is brighter to your eye. We're talking about optics or light. Or they'll create something which is dark. And that's how things get imaged. That's what the lens does. So what the lens does, is it is shaped in a way that this ray, so they start off, let's look at, again, these two waves now, this red one and this red one. They start off at the same phase, but they travel different distances and along different paths. And so the one that goes along the top goes further and comes back. The one that goes right through the center doesn't go as far. However, the one that goes the longer distance also goes through a smaller thickness of glass. The one that goes through the center travels a shorter distance, but it goes through a thicker, larger thickness of glass. And it turns out in glass, the wavelength gets smaller. When you're in a medium, the wavelength actually gets smaller. And so basically what this lens does is it's basically controlling the relative phase between these two waves such that when you come back to this point, they're actually in phase. Okay? So that's what I'm trying to show here. That all the waves that come back to this duck's point, the reason why you get an image of the duck's head there that's conjugate, or that mirrors basically what's going on over there, is because all the lens is shaped in a way that the waves that come back together here are all in phase. The problem is that if I move not all the way down to the duck's middle, but I just move down to like the duck's eye, well, that distance between the duck's eye and the duck's head is not very much different. In fact, it's smaller than the wavelength of the light. And so the duck's eye will also at this position, which should be the duck's head, some of the duck's eye will also be imaged in that place. It'll be blurred out. So the wave nature of the light basically leads to blurring. And we can characterize this. We call this the resolution limit, or sometimes it's called the Abbe limit, diffraction limit. And basically D is the smallest distance that can be between 2 points on an object, or the smallest structures that can be resolved. And you can see that it's proportional to the wavelength of light. So the shorter the wavelength, the smaller objects you can resolve. And it's also proportional to basically this thing called the numerical aperture at A, which is n sine theta, where I've defined theta here as sort of the maximum angle which can be captured by the lens. So that has to do with the size of the lens and the distance between the duck and the lens. And little n is the index of refraction. It has to do with the material. Okay? And this this rule, this law, this physical limit, was actually written on Ernst Abbe's headstone, when he died. And this is, so you can't read it, but it's in there, this right here. And it was always thought for many decades to be basically a fundamental limit to how well you can resolve things using light microscopy. Another way of thinking about this is if you've studied the double slit experiment from Young, when you have two sources of light, and I think this is pooped out. Where is it? There it is. Two point sources of light, like two molecules, as I said, and they each emit sort of radial waves or circular waves, spherical waves. You get a pattern. You can see with your eye, especially further in the back, you can see this pattern of light and dark bands. Does anybody have a laser pointer? You can see this pattern of light and dark bands, you know, when you just look at this. You can see dark band, light band going off at different angles, and that's these interference patterns of these two waves, and it has to do with the phase of the wave. And I can show this to you in a different way. So what am I drawing here? I have a point source. Okay, this is the center of the wave, and it's like you dropped a pebble into on the surface of a lake, right? A very calm, flat lake. You drop a pebble in. What happens? You make a disturbance. That disturbance propagates outward in a circular way or a spherical way. That's kind of what I'm drawing here. But we're imagining that these are light waves, and we're imagining that I've taken a picture of this at a particular point in time, because we know what happens with the pebble, right? These things propagate outwards, right? So I've just taken this picture at one particular time. And that's kind of the ripples that have been left behind by the pebble. Okay. Now, if I make another pebble nearby, or another disturbance, or another point source, then these waves that are from one and the other start to overlap with each other, and they start to interact with each other, and they start to interfere or superimpose. Okay. And the pattern that results from that depends on how far apart they are. So you can see as these things get closer and further away, you can see this pattern of bright and dark bands that are radiating out, and the angle of those changes as the two things get closer and further apart. So for example, when the two things come close together, initially these bright and dark bands are very narrow and they're very close together, and as the two objects get very close together, these bright and dark bands separate, they get more easy to distinguish. Okay, so here's an example where I've frozen this at a particular point in time, and you see this dark, bright. You can see this pattern, and you can see that for this particular separation, I have a particular pattern. Okay, so one of the key messages that you should this is kind of a very subtle and very I'd say sort of deep physics kind of message is that if you want to know, using light waves, using these waves that I'm drawing here, how far apart these two objects are, you have to be able, using a lens, you have to be able to measure this pattern. You have to be able to measure the pattern of bright and dark bands, because if you know the wavelength of light, which is the distance between successive peaks here, if you know that, and you measure this pattern, that is as a function of angle, how far, what's the angular difference between the angular separation between the bright and dark bands, you can deduce how far apart these two objects are. Okay? And the problem with using lenses, right, is that lenses have particular sizes. And so if I put my lens far away, for example, a particular size lens far away, let's imagine this is a lens now, or a camera or something, then you can measure these bright and dark bands pretty easily, because you have a big enough detector, a big enough sensor to be able to capture this pattern. Right? But if I put these two things closer together, the pattern spreads out, and now instead of having several what we call fringes, or several interference, this pattern being kind of closely spaced, now it spreads apart and I don't capture it as much, and I have much more uncertainty. Since I can't identify nearly as well exactly the location of this dark band and exactly the location of this dark band because they're broader now, then I know with less certainty how far apart these two things are. There's a correlation. Okay? If I make a detector which is even smaller at that distance, right, now I can't resolve that pattern at all. All I see is kind of a diffuse bright spot in the middle, and I can't say anything or very little about how far apart these things are. Okay? Now, if I take that small detector, that small lens, and I move it closer, now all of a sudden I can capture more of that pattern again. Okay? So my point here is that there is a relationship between the size of your lens and how far away it is from your object to how much resolve, how much information you can resolve, how much structure, the small structure that can be resolved. Okay? And that is basically what provides the limit. So the point is that we have a limitation that we cannot resolve structures much smaller. And if you think about this, theta, and if you remember back how I defined theta, theta can at most be 90 degrees. And that's actually not even a physical situation, but it's a limit. So if theta is 90 degrees, what's sine of 90 degrees? 1. N is the index of refraction. For air, it's 1. For water, it's 1.3. For glass, it's 1.5. The point is it's on order. It's of magnitude 1. And so lambda over 2 is, roughly speaking, the best that you can do. And the reason why, and this is why I said that optical microscopes can't resolve structures much smaller than about half a wavelength, or about 300 nanometers, because if you look at the region, the optical spectrum, the electromagnetic spectrum in the visible region, so the light that we can see with our eye, the wavelengths range from 400 nanometers, close to the ultraviolet, to 800 nanometers, close to the infrared. So what we can see is all the teens. So all the colors which we see right now in front of us, those all range from wavelength between 400 nanometers and 800 nanometers. And we're most sensitive about 600 nanometers in the green. Our eyes are most sensitive in the green. And there's interesting evolutionary reasons for that, actually. So anyway, the point is that 600 divided by 2 is 300. That's where that limit comes from. Okay? So how do we get around that? And I've got 5 minutes to tell you my whole talk. So I'll only be able to tell you one way to get around that, and that's basically to use a lightning rod. Okay. So what do I mean by that? So lightning rods, right? You know, these were invented. I mean, it's attributed to Franklin. It may have been invented by other people, whatever. Franklin was very aggressive at doing patents and stuff, so it could be somebody else that actually invented this. But you know, we've seen these around. They're basically rods or sticks that are kind of pointed often at the end. And what are they there for? I mean, what's the purpose, right? You know, if in a storm, in a thunderstorm, you get these big thunder clouds, and what we typically see is what's close to the surface, right? We see the cloud close to here, but actually thunder clouds, one of the reasons why you get lightning is because there's all this because of the temperature differences and things and the conditions, you get this sort of convective flow of the air in the thunder clouds, and basically that leads to a kind of friction where the molecules in the air sort of get ionized. And so now you're creating positive and negative charges through this kind of convective friction kind of flow. And so what ends up happening is that you end up getting kind of negative charges building up near the bottom of the surface, near the bottom of the thundercloud. Positive charges really high up there. And then because there's negative charges at the bottom of this cloud, and the cloud is not that high off the ground, you actually, you know, the Earth has lots of ions in it too, and you basically get positive charges which kind of are pulled towards the surface of the ground. And now you have positive charges, kind of, and sort of a surface up here, and negative charges on the surface up here, and positive charges on the surface down there. So what does that look like to those of you who have taken 2220? Maybe look like a capacitor, right? So you have, you know, negative charges. Imagine you have two metal plates, okay, and you have positive and negative charges. Well, what's the electric field in here? If we drew electric field lines, we would draw them kind of straight like this, okay? And if you take a positive charge and you stuck it in here, it would accelerate upwards. If you took a negative charge and you put it here, it would accelerate downwards. In the same way that when you drop a ball, it accelerates downwards. This is an electric field instead of a gravitational field, but the physics is the same. And so what a lightning rod does is, if you can imagine, if I take this drawing, and now instead of putting a flat plate there, I make this a very curved surface. You can imagine what's going to happen. So there's negative charges there. Negative and positive charges attract. So what happens is that the positive charges, instead of being distributed equally along the surface, concentrate near the closest point. And that's going to change these field lines. So now the field lines are all going to sort of go towards the highly curved surface. And what that means is the electric field density, or the electric field, the voltage, the electric field is just more intense there. Why is that important in lightning rods? Because it takes the air around it, and it basically ionizes the air. And now that you have ions, you can create electric paths. So right, in order for electricity to flow, in order for for electric current, you basically need low resistance. And when you basically take neutral air is an insulator. Like you can't pass electricity through neutral air. It's basically an insulator. But as soon as you make it into an ion, as soon as you basically break it down, and instead of having oxygen, diatomic oxygen, you have some sort of ion. Now you have free electrons and free protons, which can actually move. And so the purpose of a lightning rod is basically to create a plasma because of a high intensity electric field that's concentrated at the tip of the rod. At the tip of that rod, and that makes it more likely for an electric discharge to go through the lightning rod rather than your house, rather than some other nearby structure. Okay, so we use the same physics to do high resolution optics. We basically take a sharp tip, but now this is manufactured in a nanoscale way or a microscale way, so it comes to a really sharp point. And instead of basically having a thundercloud, we basically shine a laser beam on this. And what happens is that the laser beam gets concentrated, or the intensity of the laser gets concentrated at the end of the lightning rod. So that's what's meant to be this bright color here. And it gets concentrated into an area which is much smaller than half the wavelength. In this is a simulation, and when we did the simulation, we used light with a wavelength of 532 nanometers, and you can see that this is much smaller than half of that. Okay, and so you can using the sharp. Basically the sharp tip acts kind of as an antenna to help concentrate the light at the sharp point, and then what you can do is you can move that sharp point and move that high intensity region over on a sample that has features or structures that you want to measure, and you can do interesting optical microscopy. So this will be my last slide since I've run out of time, but this is kind of the cool thing. So here's people that use this idea to do biology, to do biological studies. So they basically took a part of a cell, which is called the membrane, which is only about 2 nanometers in diameter. And in the membrane, in the cell membrane, there's a lot of proteins, a lot of structures that are actually floating around. The membrane is almost like a two-dimensional fluid, and there's lots of things that are floating around in it. And they wanted to understand how close together this particular kind of protein was to each other. So basically, what was the density of these proteins, these particular proteins floating around in this cell membrane? And they were too close together to measure with a normal optical microscope. So what they did was they used a normal optical microscope to actually image this. So here's kind of a zoomed out view, so a 5 micron scale bar here, so this is 5 micrometers. And they're using light, again, the resolution limit should be 300 nanometers or so. So they imaged this little part. These are different individual cells using a normal microscope, and they sort of zoomed in on this little area there, okay? And using just their normal optical microscope technique, just with the lens, then this is sort of the structure they did for this region. This is sort of what they imaged. And this is not good enough to answer the question which they were asking. But then they basically brought their little sharp tip. In this case, it was a little gold sphere, but the sphere was about 30 nanometers in diameter. And they brought it close to the surface, okay? And then they did it again. And now this is the same exact region, and now you can see all the structure that they can resolve. And each one of these little points of light is a single protein molecule. And the question was, like, how close are they together on average, and what's their density? Here you can't say anything about that. Here you can clearly answer that question pretty easily. And that question has a biological relevance. It actually has something to do with the functioning of the cell, right? And so it's an important question to ask. And you can see that instead of 300 nanometers, they can resolve each of these little points with about 50 or 30 nanometer resolution, basically just by using this little sharp tip. Okay? So I could have talked about a whole bunch more stuff, and I'm happy to talk to anybody that's interested. But this is one of the things that we do in our lab. We have a microscope. We've built a microscope like this that has a sharp lightning rod point. It's coupled to a normal lens-based microscope system, and when you put them together, you get much higher resolution images. Okay, thanks a lot, folks. I'm happy to spend some time if anybody wants to chat. Have a good day.
So, I'm interested in calling out what's in the text.
Yeah.
Just like
Well, I think you can. I can give you some of our papers, but our papers are not. They're targeted towards people who are working in the field, so they're not really explanatory. But you can look up things like tip enhanced optical microscopy. You can also near field. I didn't, near field optical microscopy. So the reason why we call it near field is because that the size of that enhanced region is much smaller than the wavelength. You can, and there's more than one. I showed you sort of sharp tips. Another way that people do this is that they make a small aperture. So it's like opaque, and then they make a small aperture which might be 50 nanometers in size, and they force light through like a hose, and what comes out, and then they put that very close to the surface. Those are probably the two things which are most. But of course, also just come and talk to me.
And the other thing is that we talked a lot about the nature of light, especially optical light.
So
What are the limitations of using a different wavelength, like using ultraviolet?
Yeah, that's a great question. So of course, the smaller the wavelength you go, the better it gets. The better.
Mess it up.
Well, I think there's a lot of problems. So first of all, it's the kinds of laser sources and light sources that we have that we can control easily and are mostly invisible, and that's a whole nother it's a whole nother physics / technical problem. But there are becoming more and more. We are getting more and more ultraviolet sources and X-ray sources and things like that. But then the other problem is that